Chapter 12, linear regression and correlation. So let's go ahead and just begin here. So the first thing is I want to define what a scatter plot is. A scatter plot has ordered pairs and has an independent variable, which we consider our x variable, and our dependent variable, which is our y variable. Okay, I'm going to show you some steps how to draw it, and I'm going to show you some examples of what it looks like. So the first thing is you draw and label the x and y axis depending on the context that you're given. You plot each point on the graph based off your table, usually it's a table, and determine if there's any relationship that may exist. I'm going to show you the different types of relationships that we may see. So the first one is usually we have an x and y axis like this. It's usually the positive, and we might see scatter plots are just points everywhere. And if we see a scatter plot that looks something like this, this is what we call a positive linear relationship. Now, likewise, we could have the opposite, and the opposite would just be a negative linear relationship. You could see that it goes in a negative direction. And like the positive, it starts to form some type of line. So we'll call this a negative linear relationship. The next one we don't see too often. We won't really be using this. We're going to mostly stick with these first two. And this next one kind of looks like I guess it kind of looks like an arch or a rainbow of some sort, you might want to say. This is what we call a curvilinear relationship. And this next one we will also see sometimes, and this is probably a common one that we'll see as well. You can see, look, it kind of just looks like they're all over the place. What does that exactly mean? Well, that means that there is just simply no relationship. Okay, so again, the ones that will most frequently be seen are positive linear, negative linear, and then no relationship. So correlation coefficient. A couple bullet points here. First one is the population correlation coefficient, and we use the Greek letter rho. It looks like kind of like lowercase p, but we say rho. And that's the correlation computed by all the possible pairs of data values taken from the population. And the next one is the linear correlation coefficient, and we use that to be our R. It's computed from the sample data measures that strength and direction of a linear relationship between two quantitative variables. R is the correlation coefficient we will use a whole lot. The population correlation coefficient, we will use that more when we start to prove, when we write our hypothesis, our null and alternative hypotheses. Now, the relationships between the correlation coefficient and the scatter plot is that we might see something like this. Okay, we might say that, I guess I'll show you a couple different things. If I just drew a number line, we had 0 here in the middle. We had -1 and 1. You're going to find out here, I think on the next slide or a couple slides later, that our R, our correlation coefficient, is between -1 and 1. If it's -1, that's a strong negative correlation coefficient. If it's +1, then it's a strong positive correlation coefficient, and they're both going to be linear. So as it gets closer here to -1, that's our strong negative linear relationship. 0 is a no relationship, and +1 is a strong positive linear relationship. And I guess I could put +1 if you really wanted to. You also see things like this. Our scatter plot now, if we want to match these up, we talked on the last slide or 2 slides ago that that's a positive linear relationship. So in this case, our R might be something like 0.80. Really close to 1, not a perfect straight line. This would be more R equal to 1. If you want to see the negative side of it, be the same thing, just in a negative direction, be going down. So this might be something like R is negative 0. Maybe say 80. And the further apart these points are, like even this one looks like it's still going upward as we go left to right. So maybe this R is more like 0.50. And we find this in a formula. Here's your formula. How do you find R? Oh my goodness, looks like a lot, and it is. All right, it's not, this work's not for people who want to quit early. There's calculators that definitely do this work for you. We're going to do it by hand here. We're going to use tables to help us organize our data. So R is the correlation coefficient. N is our sample size. Okay, the number of data pairs, right? It's defined right there. And I can't get the cursor to show up, so I'm just going to circle as I talk about it. That means the sum of X times Y. This is the sum of X, the sum of the Y's. Sum of all the X squares. Sum of the X's, then you square them. Sum of all the Y squares. And then sum of all the Y's, then you square it. And notice how I bold and underline in the middle? We round to 3 decimal places. So now I want to show you how to find the correlation coefficient. You saw that formula can be very messy. There's things on it that you need. You need the sum of X times Y. Well, guess what? In our chart, we have a table, or I should say chart, our table, we have a whole column dedicated to X times Y. What we're going to do is we're going to add all those up at the bottom. Boom, that's going to be our summation. Next, we have the sum of the X's right here. So we have a whole column for the X's. We add them all up. Boom, we put the sum at the bottom. We also have the sum of the Y's we can use, the sum of the X squares, and the sum of the Y squares. Those are 5 columns that we will need. Notice how 1's make a table, 2 fill out the entire table and find the sum of each. And then you can find the value of R by just substituting those values that you get at the end. And I'll work a problem with you so you can see. Now, the significance of the linear correlation coefficient. When R is positive 1 or negative 1, there is a strong relationship. When it's 0, there's a weak, or what we say a non-existent relationship. You can't make any determination here. So 2 possibilities when R is not 0. The value of R is high enough to conclude that our relationship is significant enough between the 2 variables. Or the second thing is the value of R is just due to chance. This just so happened to occur. They had no relationship there. So testing the significance, this is going to be where we have our hypotheses. You have your null, and it says H sub naught, and we're going to say rho equals 0. That means the null hypothesis means that there is no correlation between the X and Y variables in the population. The alternative hypothesis is that rho is not equal to 0, that there is a significant correlation between X and Y in the population. Now I'm going to tell you what it means to reject a null. When the null hypothesis is rejected at a specific level, it means that there is a significant difference between the value of R and 0. When the null hypothesis is not rejected, it means that the value of R is not significantly different from 0, and it's probably due to chance. I know I just read my PowerPoint. I know you can read, but it is right there. Now, drawing a conclusion, there's 2 different methods. 1, using the p-value method, and method 2, using a table of critical values. We're going to use table 2. Table 1, I want to speak about with the using the p-value. That way, if you do get it just given to you as a p-value, it might say, draw your conclusion. Here's the p-value. Here's this, and here's that. So let me get to that. So method 1, we are always going to, in this class, use a significance level of 5%. So alpha is going to be 0.05. Okay, that's for everything. Method 1, method 2, that's everything. Okay, now method 1, if we're going to use the p-value, if the p-value is less than the significance level, remember our significance level is alpha is 0.05. So if our p-value is less than 0.05, then we reject the null hypothesis. And at the end, we will conclude there is sufficient evidence to conclude blah, 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 that there is a significant linear. Okay, relationship between, and the correlation coefficient is significantly different. If the p-value is not less than the significance level, so if the p-value is greater than 0.05, then you do not reject the null. And the main thing that changes is that you would say that there is insufficient compared to our sufficient, and that the correlation coefficient is not significantly different from 0. This one says that it is. Those are two things that change. And x and y, I noticed that we say x and y, but x and y, remember, are variables, so they're going to represent something. So we rarely will actually say x and y unless we're just given a table with no context. But if we have a context, our x and y do become contextually some statement there. So method 2, we use a table of critical values. There is a table that is in your textbook. I think it's on 2 pages, so I kind of had to type it out. You'll see it here on the next slide, I believe. It says compare R to the critical value in the table. So if R is between the positive and negative critical values, and the correlation is significant. If R is not between the positive and negative values, and the correlation is significant, and the line can be used for prediction. Trying to click here. There we go. There's your table. You're going to use degrees of freedom. Degrees of freedom is always your sample size minus 2. So my sample size is 3, and my degrees of freedom is 1. If my sample size was 12, then my degrees of freedom is 10, because 12 minus 2 is 10. Your critical values there on the right side, that's the positive and negative that I was talking about. Okay, and we'll do a problem where we will use this so you can see more of how to use this. So here's example 1. Example 1 says construct a scatter plot for the data shown for car rental companies in the United States for a recent year. Compute the linear correlation coefficient for the data, and then 3, test the significance of the correlation coefficient. Use alpha equals 0.05, so your 5% level significance. So first thing is we need to draw our scatter plot. And look, our X represents cars. Our Y is revenue. Okay. So when we go here, I just add the table here so we can draw this. Here is our Y, and here's our X. Right? Our X again is cars and tens and 10,000s. So we're going to say cars and 10,000s. And then the other ones, we have revenue in billions. So this is revenue. So now we've labeled them. Once we label them, now we decide and determine what values will go where. So we can start with our X value, and you can see our X value, our largest one is 63 and our smallest one is 8. So instead of me making a whole bunch of marks all over the place, I'm probably going to make 12, actually 13 of them. That way I can get those in-betweeners. So say 5, 10, 15, 20, 25, 30, 35, 40, 45, 50, 55, 60, 65, because our largest is 63. I could have spaced them out more, but I'm at where I'm at. Then my Y is in billions, remember, so my smallest is 1.4, my largest looks like it's 7.0. I'm just going to go 7. So I have 1, 2, 3, 4, 5, 6, 7. And I can write them 2, 3, 4, 5, 6, 7. You can write these down here too. And we could say 5, 10. You can write 15, 20, 25, 30. I'm not. I'm just going to write down here it's by 5s. So I'm not going to waste time labeling every single mark when I know that it goes by 5s. So then I just start plotting this thing. So company A says it had 63 well, it's 10,000ths of cars that it did, and the revenue was $7 billion. So you're gonna go over to 63. Remember, this was 65. So we can label that if we want to. 63 and go all the way up to 7. So somewhere like right in here. Next, we're gonna plot 29 and 3.9. So 29, so here's 20 and here's 30. So 29 and then 3.9, somewhere right in here maybe. And then next we have 20.8 and 2.1. So maybe right in here somewhere. Then I have 19.1 and 2.8. So 19.1, 2.8, just a little bit higher, a little less there too on the x-axis. 13.4 and 1.4, 13.4, 1.4, somewhere in here. And then lastly, I have 8.5 and 1.5. 8.5, 1.5, maybe in there somewhere. So you could see, if you have to make a conjecture, you would say, okay, well, it looks like it's positive. It looks like it's starting to get positive there. So we'll see what happens. So look at my table. I know I have it all filled in. I had these things on there and I guess they didn't show up, which is fine. But you can see I have to start building my table now. So if I go back here, construct the scatter plot, boom, done. Next, compute the linear correlation coefficient for the data. How do I do that? I have to finish my table. In order to compute my linear correlation coefficient, I need the sum of the x's, the sum of the y's, the sum of x times y, the sum of x squared, and the sum of y squared. So I'm going to create my table that we talked about. I'm going to fill it all in. So this right here was what we started with, right? I add my next column, x, y. So I'm taking 63 times 7. That gives me 441. Then I'm going to take 63, square it, and I get 3969. Then I'm going to take 7 and square it, and I get 49. I know it says 0.00, but that's okay. You don't have to. You just put 49. And we keep going that route. Once we get all those values, then we add straight down. So 63 plus 29 plus 20.8 plus 19.1 plus 13.4 plus 8.5. That gives us 153.8. That is the sum of x that we need for our correlation coefficient. Same thing here. I'm going to add straight down and I get 18.7. I'm going to add straight down the x times y and I get 682.77. And I do the same thing for each column. I add straight down and I have the sum right below. Once I have these, now I can substitute into my correlation coefficient formula, my R. There's my R formula. Don't forget your sample, your N. It's the number of data. So you have A, B, C, D, E, F. So your N is going to be 6. You can see I plugged everything in here. Now it becomes a calculator issue. You put this all into your calculator and you can see that R is 0.982. And if we went back to our scatter plot, remember, we made the conjecture that our scatter plot, looked like it was a positive linear relationship. We just show that R has a strong positive linear relationship, 0.982, very close to +1. So now let's run our hypothesis testing. Step 1, state the hypothesis. Rho equals 0, rho equals, doesn't equal 0. This should be an A, I apologize. To keep consistent with what we're doing in our class. Next, find the critical values. So what was my degrees of freedom? I had 6 data points, so 6 minus 2. My degrees of freedom is 4, so I'm going to go here, and I'm going to look at 4, my degrees of freedom, and this right here, this 0.811 are my critical values. So I'm going to have negative 0.811, and I'm going to have positive 0.811. You know, I'm trying to find if it falls in between. So using this is supposed to be table 12.8, we obtain the values plus or minus 0.811. Once we have that, we have to figure out, is it significant? So what is significant? What are we going to write there? So what we're saying is basically, remember, we have to get, if I got to draw a number line here, we get all the way to -1, all the way to +1. Our values here, our critical values are -0.811. Here's 0 somewhere in here, and then positive 0.811. Our R is 0.982. So where does that lie? Our 0.982 is somewhere out here. 0.982. So if you think about it, is R between the two critical values or no? No, it's on the outside. So R is significant. And because R is significant, we reject the null hypothesis. And now for summarizing the results, we will say there is sufficient evidence to conclude that there is a significant relationship between the number of cars, which is our X, a rental company agency owns, and its annual income, which is our Y, because the correlation coefficient is significantly different from 0. Now, let's define what a regression line is. A regression line is what we also call the line of best fit. And it's used to see the trend to make predictions. So what it normally looks like, let me just make sure I'm not ahead of myself here, is we might have a scatter plot. And we have our regression line, right? This is the regression line right there. What it's used to is it's used to make predictions, to see trends. So if this is the input, what's the output going to be based off this trend? Is it significant to be able to conclude the prediction and predict the future? So what we have, we do also a little differently. Let's say here's my regression line, and I have some scatter plot stuff. I'm just going to put a few here. But this right here, this is what we call the observed value. This is real data. We go straight down because we're talking about the same X value. This point right here, this is what we call the predicted value. And what that is, that dotted dashed line, that's called the residual. And the residual is the difference between the actual value, which is the observed value, and the predicted value, which we also call Y prime. So we also have an equation for this. How do we find the equation? It's fun. It's so fun. The equation of the regression line is Y prime equals A plus BX. A looks like a slew of stuff, so does B. But guess what? We've already done this. We've already found the correlation coefficient. We've already created our table. We found the sum of the X's, some of the Y's, some of the X times Y's, some of the X squares. In this case, we don't need the Y squares, but you get the idea. And this should actually be my fault. This should be 3 decimal places. All right, so find the regression line, make the table. Guess what? If you already have made, done. Fill the whole table, find the sum, boom, done. We should be done. When R is significant, so if R is significant, then we can do this. If R is not significant, no reason to use a regression line to make predictions because we can't make the prediction. So if you remember example 1, R was significant. So let's recall some things. Sample size was 6. The sum of X is 153.8, and you can read the rest. Once we have that, we just simply substitute it into what A is supposed to equal and what B is supposed to equal. There's A, plug all those values in, and for A, you get 0.396. For B, you get 0.106. So what is our equation? Our equation is y prime equals 0.396 plus 0.106x. Now, what is the point of a regression line? The point of the regression line is to make predictions. So let's make some predictions. You might say, hey, let's have when x is 10 or when x is 50 or when x is 4,678. Could do something like that. What about graphing this thing? What if we want to graph the regression line? In order to graph a line, definition of a line is to have 2 points connected. So any 2 points, so let's create any 2 points and draw this line. So I've already picked some out, actually typed it up, and it was easier just to kind of shrink it here. And you can see that we're going to use any x values. I like between 10 and 60 because remember our values were, if I remember right, oh shoot, now I can't remember, 8.6 and 60 point something. I can't remember. Sorry, I don't have it in front of me. That's why I chose values between 10 and 60. So pick values between your minimum and maximum, somewhere in there. So for example, I let x become 15, just substitute 15 in and see what happens. So when we substitute 15 in, this is our output. So here's our point now, 15, 1.986. Then we're gonna substitute 40 in. When we substitute 40 in, we get 4.636. Here's our other point. We're gonna plot those 2 points, draw the line. It's right there. Of course, this is using a computer, much easier, right? Don't have my sloppy graph, but it kind of looks the same. That's it.